Hello everyone, I'm back after a few days. I'm sorry I didn't record videos for a few days. I was on family vacation, but now I'm back. So let's actually do another problem live from LeetCode's top interview 150 problem list. So far we have solved all the problems up to is subsequence. If you haven't watched my videos on those problems, please go to my channel and check them out. The next one is 2 sum 2. Input array is sorted. So yeah, I think we did one problem called two sum on this channel, which looks like this is a variation of that problem. In that problem, we were given an array of numbers and we were given a target sum, and we were supposed to find out two numbers that added up to that target sum from the array. But the array wasn't necessarily sorted. While in this case, looks like the variation is that the input array given to us is already sorted. So let's read the problem and get all the details. Given a one indexed array of integers numbers. Oh, interesting. It's a one indexed array. I've hardly ever seen that in any problem saying, hey, there is an array problem, but you have to think of indices as starting from one. But okay, for some reason, that is the requirement in this problem. Given a one indexed array of integers numbers that is already sorted in non-decreasing order, find two numbers such that they add up to a specific target number. Let these two numbers be numbers of index 1 and numbers of index 2, where I is less or equal, sorry, 1 is less or equal to index 1 is less than index 2 is less or equal to numbers dot length. Yeah, since the indices start from 1, the valid bounds will be 1 to numbers dot length inclusive. Return the indices of the two numbers, index 1 and index 2, added by 1 as an integer array. So, okay, so the two indices that add up to a specific target have to be returned as an array of size 2. And they say added by 1 because I think it's because we are doing 1 based indices and not 0 based indices. Anyway, the tests are generated such that there's exactly one solution. You may not use the same element twice. Yeah, not using same element twice is the same restriction as the basic problem we did. Your solution must use only constant extra space. Okay, so that is a bit of a new restriction, but in this case, we are given that the array is sorted. The examples are 2, 7, 11, 15. Target is 9, so obviously 2 and 7 add up to that, but the indices of 2 and 7 are 0 and 1. But we add 1 to it to make them 1 based indices and return 1, 2. Makes sense. The second example is 2, 3, 4. Target is 6. 2 and 4 are indices 0 and 2, but we return 1 and 3 to make them 1 based indices. And then finally, minus 1 and 0. Target is minus 1. Yeah, they add up to minus 1. So indices are 0, 1. To make them 1 based indices, we make 1, 2. Constraints are the numbers dot length, the size of the array is between 2 and 30,000 inclusive. Okay, the value in the numbers array are between minus 1,000 and 1,000 inclusive. Numbers is sorted. We are given that obviously, and then the target sum is also between minus 1,000 and 1,000 inclusive. And the tests are generated such that there is exactly one solution. Okay, sounds good. Well, I mean, let's begin from the basic problem is solved without the restriction that the array is sorted or without the property that the input array is sorted, right? In that case, we explored a few approaches, right? We explored an n-square approach where for each number in the array, we could look at the remaining numbers on the right side and find a complement number in linear time. And as in find the complement number in linear time, and the whole algorithm becomes n squared. Then we explored an approach where we could actually take the time to sort the array in log n time. And once the array is sorted, then for each number, finding its complement becomes log n time, making the whole algorithm n log n. And then finally, we use the extra memory and use the hash table to store all the numbers, and which can be done in O of n time. And then the complement of a specific number can be found in O of 1 time. And hence the algorithm becomes O of n. If you haven't again watched that video on this channel, please go and watch that video. It's called 2 sum. In this case, the thing is we cannot use extra memory, right? And they have, but they have given us that the input array is sorted. So what can we do? Well, the one thing we can do is we can actually make use of the property that the input array is sorted and at least make the algorithm and log it, right? So basically, given an array, for example, let's take an example from here. Given numbers array like this, we can actually scan through each number, for example, 2, and take the remaining subarray, and in log n time by doing binary search, we can find complement of 2. In this case, the complement of 2 is 7 because the total target is 9, right? So that can make the algorithm n log n. So we can definitely do that. Uh, and we don't need to sort the array because the array is sorted, right? So we have an O of n log n approach is as follows, right? For each element in numbers, find the complement with binary search in the remaining array, right? Remaining array. So that's the approach we could take, and we could just return the result. Well, in this case, the thing is though, I don't like the fact that this problem is already, like if you see here, categorized under 2 pointers. And that's because I think it already gives me a big hint saying, oh, there is actually a better approach which includes 2 pointers and somehow can be done in linear time. And I think as soon as somebody says that, it's like the biggest hint. And if this was asked in a real interview and they were not giving us the hint, then I'm not sure if it will be so quick for us to get that idea, right? And the idea is very simple, actually, thinking about it. That we start with 2 pointers, right? The left pointer is 0, right pointer is pointing at the last element in this case. Let's add a few elements here. I don't like the fact that it's a very small array, right? So let's say 17, 25, 80 and 100, right? And then let's then let's say the target is actually 27. Okay, I don't know if there is exactly one solution as is for 27, but I'm just going to take it. So R is equal to what? 1, 2, 3, 4, 5, 6, 8. So R is 7, right? That's the last index. We start from 0 and 7 and we look at the sum, right? What is the sum of the elements at 0 and element at 7? Well, it's 102, right? And what is our sum? So let me say a sum equal to 102. And the target though is equal to 27, right? So our target is smaller. Well, how can we become smaller? By moving the right pointer one this way or by moving the left pointer one this way? Well, we have to move the right pointer one to the left so that we get a smaller number to make the sum smaller, right? So that's what we do. We move the right pointer to 6 and then we say sum is equal to, what is the sum of 0 and 6? That's 2 and 80, so 82. And then t is equal to still 27. That is our original t. And so that is still bigger, and so on and so forth, right? So we say, okay, let's actually try to finish this example. We reduce the right pointer. We say, now what is the sum of the 0th element and the element at index 5? Well, 0 is 2 still. Index 5 is 25, and that's exactly 27, right? And then that is our answer. So we just return that, right? Return here. And if we do this approach, and if at all we became bigger, if we were smaller than the sum, then we would actually move the left pointer, right? If that happened. So for example, if the target was, let's say, 25 plus 11, so 36, then we would be moving here. All of these are target 36. We would still be doing, moving the right pointer in the first two iterations, but in the third iteration, since sum is now lower, we are going to move the left pointer forward. So, but R remains at 5, right? And that's because we want a bigger number from the left side, right? And so, okay, so from the left side, we get a bigger number, well, 1, and so the sum is 7 plus 25, and that is 32. And target is still 36. So target is still bigger, so we keep moving left. And finally, at L equal to 2, R equal to 5, we are going to find the sum 36, right? And target is 36. So that's our algorithm. Unfortunately, they gave a big hint by categorizing the problem under 2 pointers. which I do not like, but I cannot unknow what I already know. So not sure what would have happened if they did not do that. Okay, let's try to implement this approach. It's actually going to be very, very simple in code. There isn't much to figure out in code. We basically do left and right. We write a loop until left is less than right. So let's do that. Left equal to 0 and right equal to no, so not target, but numbers dot length minus 1, and then while left, sorry about that, is less than right. And what we do is we just figure out the sum first, right? So sum equals numbers of left plus numbers of right, and then we come, there are three cases, right? If the sum is equal target, then we return, right? We return new array of size 2 where we do left plus 1, and remember the indices have to be incremented by 1 to make them one-based indices, as the problem already said, right? Else if sum is less than target, which means the target is bigger, then we may need to make the sum bigger, right? And in order to make the sum bigger, we do plus plus left, right? And else we do minus minus right. This is exactly what we did earlier. And then outside, if we haven't returned yet, well, they are guaranteeing that there will be exactly one solution, but we have to make Java happy. And it's also a good practice. We should actually have, some dummy value saying, hey, -1 or 0, 0 as invalid indices being returned outside, right? That is actually pretty much it, I think. Yeah, I think so. So let's run that and see what happens. Okay, there you go. So that's that. I am going to add the one that I used. I always do that. The one that I used to come up with my algorithm as one of the test cases. So let's do that. Let's add this. And then as a test case. Okay, and then target is 36. I like 36. That moves both left and right at different times. Okay, there you go. Makes sense. Okay, so now let's try to submit this and make sure that the bigger suite of test cases actually works on it, and also to kind of see idea of our performance. No, not today. Okay, there you go. So it did get accepted, which is good. And then we are about 90% in terms of beating everybody else. And memory doesn't mean anything. I don't know why it just beats 5%, but I'm assuming most people's memory consumption for this linear approach is very similar to ours. Time also kind of doesn't mean much. I mean, most people's implementation should look similar. Hopefully that was helpful to all of you. Again, sorry for the small hiatus while I was on vacation recording these videos, but I'm back and I plan to record more of these videos every day. Hopefully this was helpful. Please hit the subscribe button on the channel or like button on the video or both. I'll see you guys next time.